Hi everyone, today we're going to be looking at NMR spectroscopy. Now I have a few things up on Blackboard already from the start of the semester. I have this visual guide here for 1H NMR or proton NMR, and I have also another one on 13C NMR. I also put up a link to Khan Academy and discusses in great detail the theory behind NMR spectroscopy. So today what I'm going to do is look at the theory and start then applying the theory to our unknowns. So NMR spectroscopy is a very important analytical technique and it's used to identify what we're going to learn is the environments of the hydrogen atoms in the molecule and the carbon atoms in the molecule. And it's all based on the fact that some atomic nuclei, for example 1H and 13C, all possess this thing called a spin quantum number. So now only those, some molecules don't possess them. So what I'm going to do is going through the theory now. As I say, this is very general. There's more specific details in the Khan Academy. So we look first at our 1H NMR. So if we look at the atom of a hydrogen, it has one proton and one electron. So we're going to be focusing on the proton, and hence this is called, or is often referred to as proton NMR. So the proton is spinning. So that's our original atom there. So we have, in the middle we have the nucleus and our electron. But within that nucleus then, our proton is spinning with the nucleus, or within the nucleus. So if you want to think about it, the proton's in here and it's spinning round, 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 round. Now, it can be spinning this way or it can be spinning that way. Okay, both directions. But any time, any charged particle that spins produces a magnetic field. So the proton is in here, spinning and spinning around either this way or spinning that way. It's going to produce its own magnetic field, and that's very important. Now, normally magnetic fields of protons are orientated at random, okay, so there's no specific order. But we have that proton spinning away by itself, and what we're going to do then is apply an external magnetic field. So now I'll be taking pictures of all these and uploading them also, of these notes. So if we take that hydrogen atom, specifically the proton and the magnetic field that it has created, and we apply a strong external magnetic field to it, something's going to happen to it, right? The proton will either line up with or against or opposite to the external field. Now, if it lines up with, that's referred to as alpha, and if it lines up or flips or spins against, it's beta. So if it's already lined up with the external magnetic field, we only need to apply low energy, whereas if it's against, we need high energy. Now I'm going to write here the difference in energy is radio wave frequency. So protons absorb the radio waves at the frequency corresponding to the energy difference, this energy difference, and that's called resonance. So bringing something into resonance means applying the energy, sufficient energy it needs to flip the proton. The key thing here is, and this is the key concept behind this whole NMR spectroscopy, the energy required to make a nucleus spin against or opposite direction to the external magnetic field is dependent on the environment the nucleus occupies, and thus can provide information on the structure of the molecules.